Hello and welcome. My name is Moxey from Wolfspeed Power, and we're here to discuss how the silicon carbide market is being enabled through quality and long-term reliability. Silicon carbide as a technology may not have had the 60 to 70 years of legacy that silicon has, but it's certainly not a new and proven technology. In actual fact, silicon carbide is in use in the market all around, from power supplies to electric transportation, through to solar and energy renewables, through to many industrial type of applications. So it's widely recognized that silicon carbide has transformed the power industry. It's mature, it's proven, it's accepted. So the conversations today with the customer base are no longer what is it or how do I use it? The questions now are pivoted somewhat to what is the long-term reliability of this technology and how can I ensure getting continuation of supply? So why are we talking about silicon carbide quality and long-term reliability? Let's just take an example of the biggest exploding market for silicon carbide, which is battery electric vehicles, onboard charging and drivetrain. As you can see here, independent data shows that up to 45% of all BEVs will be using silicon carbide in their inverters within the next 4 years. Some people say up to 70%. So these end systems are ramping silicon carbide in mega volumes. These will be household names of automotive vehicles, transitioning their major parts of their portfolio and their reputations into silicon carbide. So planes, trains, automobiles, the demand at component level will be all about automotive quality, outstanding quality, but also long-term reliability. Look at electric vehicles, look at trains, look at other applications, heavy industrial applications. They have 10 to 15 to 20 years of life cycle. Customers want to know what will silicon carbide be, the long-term reliability, not just after 1,000 hours of qual, but 5 years, 10 years, 1,000,000 miles of driving, etc., etc. So what does the industry do and why do we do it? Two things happen: qualification testing and reliability testing, because qualification doesn't equal long-term reliability. Qualification, or qual, is a very rigorous series of tests against rigorous standards, typically for 1,000 hours across multiple different lots, that demonstrate minimum outgoing quality and early life failure percentage. Qualification is all about lot tolerant percent defect. This is where we can basically get confidence of less than 1% failure from an outgoing qualification. But what happens after that rigorous 1,000 hours? Reliability testing. This is where we're designed to demonstrate the long-term wear out of lifetime that can be expected. I want my car to run 1,000,000 miles, 1,000,000 kilometers. So here we look at mean time to failure, MTTF, time to 1% failure. Here we extrapolate rigorous testing well over datasheet values to point of failures, and then extrapolate back to get a statistical gauge of how many hours the MTTF for a particular part at normal usage. We can't obviously run a part for 30, 40, 50 million hours and wait. So this is where we push them beyond their limits and then extrapolate back. Doing this, TDDB, time dependent dielectric breakdown, for our new generation 3 of Wolfspeed MOSFETs, the MTTF is 30 million hours. So what does the industry actually look at? It's what's commonly called the bathtub curve. This has been entrenched within silicon and now is very much entrenched within silicon carbide. What we're referring to is really decreasing failure rate from launch, constant failure rate during field usage, and then the increasing failure rate at the right-hand side of the bathtub as the part wears out over many, many years. At launch, for qualification and after qualification, you're there to weed out the problems, the teething problems. So this is rigorous qualification, safe launch. Here you're weeding out those early failures. You're going to see initially a higher failure rate at launch, but rapidly weed those down. Then when you get to steady state, the constant use period, which is any time up to 5, 10, 15, 20 years, depends on application. This is where you get your steady state low fit rate of failures. This is all down to proven field hours and fit rate. Then as the product becomes old within its application, like anything, you're going to see some wear out mechanisms. This is intrinsic reliability. And this is where the extensive Wolfspeed long-term wear out studies and data have come into effect. So extrinsic at launch, observed during steady state, and intrinsic long-term wear out. The question's now, how does silicon carbide relate to extrinsic, observed, and intrinsic reliability? One of the biggest causes of long-term reliability questions against silicon carbide and silicon, to be quite honest, is blocking voltage. How long will it block that battery voltage, mains rectified voltage, DC solar panel voltage across the device reliably? What are the failure mechanisms? Edge termination breakdown being one of the main ones, gate oxide. Silicon carbide itself breakdown. Epi layers, defects, inversion layer mobility, gate dielectric, edge termination, implanting, doping, ohmic contacts. High blocking voltage can be potentially the cause of failure around the edge termination in the SiC drift layer or at the gate due to the very high electric field of silicon carbide technology. To test the mechanisms at Wolfspeed, we perform high temperature reverse bias and what we call accelerated high temperature reverse bias to test the actual time to wear out failure. Now add humidity into the mix of blocking voltage and it brings a whole slew of problems. Think about silicon carbide enabling the renewable energy sector where string inverters, microinverters are outside in very high humidity environments, very saltwater environments if it's near the coast, very high humidity if it's in the humid area, Southeast Asia, for example. So adding that extra humidity really causes problems. So here we don't just have temperature humidity bias testing. Wolfspeed has introduced a rigorous temperature humidity bias testing at 80% blocking voltage. The JEDEC standards call out for 100 volts across the device. Well, these are 650, 1200 volt rated devices, so 100 volts across the device doesn't really test them to their limit. THB 80, implemented by Wolfspeed, is 80% rated voltage across the device. So we have realized how the market needs high humidity reverse blocking in addition to standard reverse blocking. Another way Wolfspeed is pushing the limits of silicon carbide to prove the long-term reliability. In addition, gate voltage blocking and strength. You have gate oxide breakdowns, dielectric breakdowns, threshold drift, all phenomenon for MOSFETs generally, silicon and silicon carbide. So what do we do to prove the long-term reliability? We do accelerated testings on time dielectric breakdowns, high temperature gate switching, positive gate bias, negative gate bias to measure breakdowns and shifts. As we have determined, extrinsic reliability is all about the product qualification stage. So what are the standards of qualification for silicon carbide? Well, not surprisingly, they're a legacy carried over from silicon. Silicon has been used in JEDEC and AEC-Q for industrial and automotive for many years, and that is what the silicon carbide industry has adopted. JESDA 22, JESDA 47 for the JEDEC industrial standard, and then AEC-Q 101, which is now Rev D for automotive. And the SiC community can only use these standards that we have. We are adopting and interpreting them for these against the existing standards for the needs of the silicon carbide technology and the customers themselves, because silicon carbide is not silicon. All these standards bodies are developing silicon carbide specific standards, JEDEC, IEC, AEC, JITA in Japan, and Wolfspeed is leading the path within these standards committees to ensure that the correct standards are adopted for silicon carbide. So extrinsic reliability is all about qualification. Then we move to that long, flat bottom of the bathtub, the observed failures, the steady state region. This is all about field reliability. This is about products in the field performing as they should do, reliably, consistently for year after year after year. At Wolfspeed, we track our field device hours in billions of hours, following the usual industry standard way of tracking. And then we calculate the fit rate of those products, again, against the industry regulated ways of calculating fit. And right now, Wolfspeed has the advantage of being in the silicon carbide business for pretty much the longest time and having the most widely diverse product portfolio. So numbers of products sold times numbers of hours they were sold for is the field hours in billions. And as you can see, we have split out by our family, C3D diode family, C4, C5, C6 diodes, C3 being in the field for the longest amount of time, sold the most amount of parts, right through to the C6D series of diodes that were released several months ago. Hence you can see the billions of field hours, nearly just under 5 trillion field hours of C3D diodes compared to a relatively short period of time for C6D. Then we have the MOSFETs, the C2M, and then the C3M series. The C2M was released 5.5, 6 years ago. The C3M was released 1.5 to 2 years ago, still releasing and proliferating products now. And as you can see, in total, Wolfspeed has just around 6 trillion field hours of product in the market, way more than any other silicon carbide supplier. From that, we calculate the fit, and the fit is in parts, devices per billion. And you can see all of the fits are incredibly low. The vast majority are in single digits, the C6D being the most recent released, and those extrinsic failures. But fit rates, if you average them out, are below 5 fit. That's 5 parts per billion. So Wolfspeed, with 6 trillion field hours in the market and a fit rate below 5 parts per billion, proves consistent long-term reliability through the observed steady state usage period of products. Now, interesting, what would actually be detrimental to those products externally to the products themselves, outside of normal wear-out mechanisms? Cosmic neutron irradiation, single event burnout, is a phenomenon getting a lot of attention right now. And we at Wolfspeed have mapped and studied this in great detail. We can categorically say for terrestrial neutron, silicon versus silicon carbide, all silicon carbide has more immunity to terrestrial neutron than silicon. IGBTs show a sharper failure in the onset and then a higher failure, max failure rate, whereas silicon carbide has a lower long-term fit rate against cosmic radiation than silicon. It's very useful to take long-term studies for the observed failure rate portion of the bathtub. And at Wolfspeed, we've developed a reliability bathtub curve calculator. This is where we mission profile the device parameters, voltage breakdown, VDS, VGS, junction temperature, altitude, all of those factors, and put them into a reliability calculator against field years and parts per billion. We don't model yet time dielectric breakdowns, early life failure rates. These can be added, but the standard parameters affecting observed failure rate, and it can be seen across our MOSFET profile, taking into account alt HTRB, TDDB, terrestrial neutral, that we model those, and at a fit rate of under 10, we come out to be 1,000 field years result. 1,000 field years modeled at under 10 fit rate. Now let's move to intrinsic wear out. So the final wear out mechanisms at the end of the lifespan of these silicon carbide parts. Here we have to do extremely rigorous extended lifetimes, push to destruction, and then extrapolate back for normal operation, because we simply cannot work a device for millions and millions and millions of hours. This is adopted again from the silicon industry, so this is standard practice. Here we show Wolfspeed C3M MOSFETs. We show drain voltage, VDS, on the left-hand side, and we show VGS on the right-hand side. Here we push a large lot size of devices to absolute destruction over voltage, and then extrapolate back to see expected field lifetime. On VDS, breakdown, these are typical 1200 volt parts, C3M MOSFETs breaking down at 14, 15, 1600 volts, and then we extrapolate back to normal blocking voltage of 800 volts. And here we show a lifetime expectancy of somewhere around, lots of zeros, 300, 400, 500 million hours, depends on what voltage it's blocking, between 700 and 900 volts typically. 300 million hours. And then on the gate voltage, again, taking a large spread of devices to destruction. This is a 15 volt rated device, and destruction at 30 to 35 volts. We extrapolate back, and we're getting at rated voltage, which is 15 volts, somewhere in the region of 50 million hours of expected lifetime at the gate voltage. So qualification and long-term reliability, check. Wolfspeed has extensive experience in all qualification, has over 6 trillion field hours of product in the field, and has extensive long-term wear out studies to ensure long-term reliability. So now, reliable, yes. Supply. Let's look at supply, because the silicon carbide market is expected to grow greater than 10x over the next 5 years. Automotive takes the vast majority of this chunk, but not only automotive, renewables, traction, industrial, power supply, all of the markets are booming in their need for silicon carbide. So not only do we have reliable products at Wolfspeed, proven reliable products, but also we're investing $1 billion in the world's only state-of-the-art silicon carbide fab. And this will increase our capacity over 30x from where we stand today.